Hello everyone, my name is Jonny, and today I'm presenting our work, PPipe, Efficient Video Analytics Serving on Heterogeneous GPU clusters via pool-based pipeline parallelism. This is a joint work with my colleague Qiang and my advisor Charlie, all from Purdue University. So in recent years, we're seeing there's an increasing need for video analytics applications. In these applications, cameras are deployed at places such as road intersections, highways, and indoors. And these cameras send video feeds to some server in a data center, likely a GPU server, which runs tasks such as object detection. And this in turn enables some downstream applications like traffic monitoring, traffic analysis, and crowd analysis. To make such a system responsive, it is often required that all these complete within a short time interval to meet a tight latency SLO, for example, 200 milliseconds. And so given the ever-increasing inference request and the enormous cost they incur, the system goal of video analytics inference serving is how to maximize the inference throughput of the server while meeting the stringent latency SLOs, usually in the order of hundreds of milliseconds. And also another trend that we are observing is new GPUs are released every few years with varying compute power. For example, NVIDIA releases a new generation of GPUs every few years. So what this means is cloud operators today are increasingly operating heterogeneous data centers equipped with GPUs with different compute powers. However, in such a heterogeneous GPU setup, the problem is that if we directly use individual GPUs to serve requests under data parallelism, we find that low-class GPUs often fail to meet the SLOs. So for example, in this figure, we are showing the latency of over 18 popular computer vision models on two GPUs, L4 and P4. So L4 as the newer GPU, as shown in the blue bars, serves this model pretty quickly, but P4 has on average 3 to 8 times higher latency than L4. This means P4s often cannot meet the SLO if the SLO is set at 200 milliseconds, and therefore low-class GPUs like P4s often cannot be directly leveraged in such a video analytics serving problem. And so to leverage these low-class GPUs, one obvious idea is pipeline parallelism, where we partition the model across heterogeneous GPUs so that the low-class GPU only runs a portion of the model, so that the total end-to-end latency is hopefully within the SLO. However, we find that naively doing so incurs high latency. Just for example, if the P4 is 10 times slower than L4, then if we just give 1/5 of the model to P4, this already yields 2.8 times higher latency than running the entire model on L4. To address this, our insight is there exists layer-wise latency diversity across GPUs. Specifically, as shown in this figure, we are plotting the latency ratio of each layer between two GPUs, P4 and L4. The x-axis is the layer ID of the model, and the y-axis is the latency ratio. First, we see that P4, being the older model, being the older GPU, is generally 2 times x slower than L4 on average. But note that this line is not a horizontal line, meaning there are some layers that are only 1.6 times slower, but on some other layers, the P4 is up to 4.5 times slower than L4. So therefore, for this specific model, in order to maximize the overall system efficiency, it will be best if we place the early layers on P4 and later layers on L4. However, this trend might change if we look at a different set of GPUs. For example, if we additionally plot the latency ratio on the same model between P4 and V100 as the orange line, we see that the trend of this line is opposite. This means the optimal GPU choice across layers would change. So the overall implication from this figure is that the model partitioning needs to be both GPU aware and model aware. So taking this idea, we can run it with standard pipeline parallelism, which organizes GPUs into a bunch of pipelines where each pipeline is a chain of heterogeneous GPUs. We focus on an example serving one model using a cluster of mixed GPUs. For example, the model may be partitioned into two chunks running on a chain of two GPUs. In practice, multiple such chains may exist and work in parallel, but our figure is only showing one chain. The first GPU, the blue one, being the later newer high-class GPU, likely runs more layer than the low-class GPU so that they have equal runtime. However, we find that such a traditional pipeline parallelism leads to a rigid pipeline structure. What that means is, first, it is required that the two types of GPUs have an equal ratio. There's equal count of both types of GPUs. And secondly, in order to yield equal runtime per stage to avoid pipeline stalls, in this particular example, there are only two possible choices of partition points. One is what we are showing in the figure right now, 3 layers versus 1 layer. Or if we swap the order of two GPUs, we partition in 1 layer versus 3 layers. So 2 choices in total. And this limited choice of partition points is often different from the optimal partition point to perform GPU-aware model partitioning, and is therefore suboptimal. To address these limitations, we proposed a technique called pool-based pipeline parallelism. So instead of forming multiple chains of GPUs, we make GPUs in each stage form a pool. As shown in the figure, each circle is a pool of GPUs. And then the model partitioning and the GPU placement is done such that each pool or each stage have equal throughput. For each incoming batch, they can be routed to any GPU in each pool. For example, a possible way is what's shown in the red arrows. And the advantage of this design is that it overcomes the drawbacks of traditional pipeline parallelism, because first, it allows different runtime across stages as long as the throughput across stages are equal. And secondly, it enables us to flexibly pick partition points. If the ratio, for example, we can pick any partition point, for example, 2 layers versus 2 layers, and then adjust the GPU ratio on each stage to make the throughput match across stages. If the ratio of the GPUs used doesn't match the ratio of GPUs available for this pipeline, we can generate additional pipelines as shown in the figure. So to leverage the pooled pipeline concept, the problem we're going to solve is as follows. Given a cluster of heterogeneous GPUs, how to form pool-based pipelines to serve batch inferences to maximize the cluster throughput while meeting SLOs. This problem remains challenging because in practice, we want to do batch inference in order to improve system efficiency. But for an online system, requests arrive continuously, and this causes unpredictable timings. So since the continuous arrival makes the problem complicated, we first make a simplification. We assume all the requests arrive in batches for now. For example, in the example on the right, maybe 8 requests arrive in 2 batches of 4 simultaneously at the first stage, and then they start execution. After finishing execution on the first stage, they together flow down to the second stage, where the GPUs on the first stage take as input 2 additional new batches. So with this assumption, we just need to decide on 3 things. What's the partition point on the model? What and how many GPUs to use per stage? And what's the batch size that the pipeline is supposed to run at? It turns out this problem has a simple, straightforward MILP formulation, or mixed integer linear programming formulation, where the decision variables are exactly those three things. And the objective of such a MILP formulation is how to maximize the cluster throughput. This throughput can be expressed using an equation with the decision variables, and the coefficient of that equation is from offline profiling. And also, obviously, we need to meet the constraint that the summation of latency across stages is within SLO, and also the GPUs we use is less than or equal to the available GPUs. However, in reality, since requests arrive individually, it takes time for them to form batches, and then the batch can be dispatched to the pipeline. This first causes a batching delay, and additionally, as batches are issued into the pipelines asynchronously, and as they flow down from one stage to the next, it may experience an interstage queuing delay if none of the GPUs on the next stage are available. Such timing variations are hard to model offline using a mixed integer linear programming formulation, and during online, this leads to SLO violations. So to deal with this problem, we employ a resource reservation-based adaptive batching technique, which dynamically form batches and dispatch them down the pipeline, such that the SLOs are always met. This boils down to selecting three things. First, what batch size of a batch to dispatch? And secondly, which pipeline to dispatch to, for example, as shown in the blue arrow. And thirdly, what paths in the pipeline should the batch go through, as shown in the red arrows. So to achieve this, at a very high level, we bookkeep which resources will be used by every on-the-fly batch. So we bookkeep both the GPU and network resources. And so with this information, for each new batch, we know which resources are available and when. This enables us to search for a pipeline and pipeline path that gives the earliest completion time. And if the fastest path still cannot meet the SLO, we reduce the batch size and retry. And this is a very high-level overview. Please refer to our paper for the details of the algorithm. We evaluate our system on a simulator with 25 high-class GPUs and 75 low-class GPUs with various configurations. And we also have a real implementation running on Google Cloud with 16 GPUs with 4 high-class GPUs plus 12 low-class GPUs. The bandwidth between the pairwise bandwidth between every two hosts is taken from what's available on Google Cloud. We evaluate our system across a diverse set of computer vision models, primarily consisting of object recognition, object detection, and segmentation. We compare our framework with two baselines. The first baseline, NP, represents the class of works that doesn't do model partitioning. And another baseline called Delta R does model partitioning, but in the traditional chained pipeline manner, not the pooled baseline, not the pooled pipeline. We issue realistic request workload into the system, and we look at two metrics. First, the SLO attainment. That means what's the percentage of requests that are successfully served, where success means the request is not dropped or not violating the SLO. We also look at the max load the system can support under 99 percentile SLO attainment. So here we show 2 out of 4. We show the result on 2 out of 4 cluster configurations, where x-axis is the load and the y-axis is the SLO attainment. We show that as load increases, the two baselines quickly see a drop in SLO attainment. However, PPipe consistently maintains 99 percentile SLO attainment, achieving 48% and 32% higher max load than the two baselines, respectively. And to understand where this gain comes from, we look at the GPU utilization for both separately for high-class and low-class GPUs. We find that for high-class GPU utilization, the three frameworks, two baselines and ours, achieve close to the same utilization, close to 100%. But the difference lies in the utilization in low-class GPUs. So the two baselines and ours achieve low-class GPU utilization of 8%, 30%, and 74% respectively. This shows that we can better leverage low-class GPUs. So in conclusion, we present PPipe, the first pipeline parallel model serving framework for heterogeneous GPU clusters under SLO constraints. It primarily encompasses three designs. First, a pool-based pipeline parallelism for flexible model partitioning. Second, a control plane which uses a MILP solver to determine the optimal pipeline structure. And third, a data plane which uses a resource reservation-based adaptive batching to decide how to dispatch batches such that the SLO is always met. It improves the low-class GPU utilization by 41 to 66% and total throughput by 32 to 75%. And that's the end of my talk, and I welcome any questions. Thank you.